Here we go. All right, so we're going to be recording. We're trying to post these on YouTube. We'll see how that goes. Um, so just keep an ear out for that. So the first thing you should have noticed, hopefully you highlighted something in this paragraph right here about independent versus dependent variables. You should be well aware of what they are, where they go, and what they represent, but I'm going to make sure you get the basics of them right now just as a reminder. So X is always, I won't say always because there's exceptions to any rule, but almost always in this class, you're going to see the X-axis represent the independent variable and the Y-axis represent the dependable variable or the dependent variable. You can really count on that variable. So it is dependent on the other variable for its change. So what that means is that the independent variable is something that you manipulate, it's something that you're controlling, or it's something that moves on its own, and as a result, it's not responding to something else. So for instance, time is always independent of everything else, and most other things are going to be a result of that changing time and some given amount of energy being applied to something. Excuse me. So we are looking at something you're adjusting or something that moves on its own accord, like time, on your x-axis, and then whatever the other variable is graphed on the y-axis. So I remind you, all graphs need to have axis labels, and generally you're going to want scaling. In these cases, I'm just looking for the axis labels for your homework. You don't need scales. If you did scales, and I noticed some people turned in scales in other classes, and it was always girls, and it was always super neat. And I actually left them a comment. It's like, "Oh, you did such a good job." But just to let you know, these are sketches. You are actually practicing sketching graphs here, which actually is just a qualitative picture. All right, you're just drawing a picture real quick. All righty. So this bit just reminds you of that, and then it shows you the correct and incorrect versions of the use of those different variables. You are going to be adjusting the temperature of a gas, and so that, because you're adjusting it, is the independent variable and thus goes on your x-axis. As you adjust that temperature, you will see a responding change in volume. In this case, you're going to see a linear increase in volume and temperature, and that would mean that there is a direct relationship between temperature and volume. So this is actually one of the gas laws. If you remember from chemistry, you've got three. You've got Boyle's, Charles, and Gay-Lussac's. All right, so the mnemonic device that I always taught my physical science students that you might remember, I don't know how you guys remember it, is that big tigers play or can play golf violently. And so the first letter in each two-letter pair is the law, and the second letter in each two-letter pair is the constant or the variable with which you hold constant. So we're holding pressure constant because you don't see it on the chart here. So this is Charles's law. So Charles's law, so Charles, you can tell us all about it later. It states that there's a direct relationship between temperature and volume of a gas held at a constant pressure. So this is just a reference to something you might recognize. We will actually see another of the gas laws almost immediately. All right, so the next thing it talks about is curve fitting. And now curve fitting can be really quickly summarized in just this one sentence. The process of matching an equation to a curve is called curve fitting. Many of you highlighted this statement, but I'm going to highlight it for you again. That is because it is simply being able to recognize what kind of a curve you're looking at and then matching an equation appropriately. And that requires you to be able to recognize one of 5 kinds of graphs. So just know that one of them you will almost never see past the first month of school, actually past the first week of motion, and then after that, everything else you'll see pretty frequently. All right, so the first formula that they give you in this whole thing is that y is equal to mx plus b. You should have this tattooed somewhere on the inside of your eyelids next to density is equal to mass over volume, and that E is equal to mc squared. These are things that you should know. All right, that last one's just, if you wanna. But the y is equal to mx plus b is something we will return to all year. It's something that we will talk about constantly, and it is something that you need to memorize. There's a lot of things I'm going to ask you to know. This is something you need to memorize. All right, and the statement says that assuming that y is a function of x, meaning that y is dependent on the function and the change of x values, the rate at which they change and where it starts, you're going to see some kind of relationship. And if it's linear, you can represent that relationship as follows. Y, the output, is equal to m, the rate of change, multiplied by some specific input of x plus your initial condition. And so what the rate of change is going to tell you is how quickly your line increases or decreases, if it's positive or negative. And the x value is going to tell you at what point on the independent variable or the x-axis you are trying to get an output. Because if you know anything about a line, when it's graphed, it's actually a compilation of multiple plotted points. And each of those plotted points has an XY pair. And what this does is, given some rate of change in where you started, for any X in an XY pair, it will spit out a Y. So the whole point of this assignment, if you've been scratching your head the whole time thinking, why am I doing this? It is to be able to make a graph a predictable equation. You want to have it in this form, and we're going to talk about how to modify this form for each of the graphs to appropriately handle something, linearize it, and then become or produce a predictable mathematical model. So the example they give you here is velocity over time graph, and you can see it has some intercept, so that's going to be some positive value. It has some defined rate that is constant because this line does not change slope, which means that it is a line and not a curve. Just a reminder, curves don't have slope. Curves have infinite slope. Just like a circle has an infinite number of straight lines that compose it, a curve is going to have an infinite number of, it just depends on how tiny of a slice of that curve you're looking at, and then you can talk about the slope between those 2 points. And we talk about that when we talk about limits and tangent lines. But the big point is you can't take the slope of a curve. That's the big point. That's the takeaway. So your goal is, if you see a curved line on a graph, you know that you cannot predictably use y is equal to mx plus b and get any information out of that data. You're going to have to do something to that data in order to make the curve straighten out. All right, and that's what we're going to be exploring today. Is what do you have to do in order to treat the data? That's what I call it, data treatment. So you're going to have to do something to one of the sets of data. It is then going to correct the curve, turn it into a straight line, and then you can find a slope. Once you find a slope, you can predict, because now you have a predictable rate of change, and we will be good to go. So this is the very first thing they show you that is not a linear line, and it is an inverse relationship. You should recognize that, but if you don't, it simply states that as one variable goes up, so in this case volume, the other variable goes down. And inverse means that exact thing. As one goes up, the other goes down. So for instance, if you hold a product constant, then in multiplication, you have an inverse relationship between the two products. So for instance, if I'm looking for the answer 10 and I have 1 and 10, if I increase the number 1, but I'm still looking for the answer 10, the second thing I'm multiplying has to become 5. All right, so if I go 1 and 10 is 10, and I still want 10, and I move 1 to 2, then the second number has to decrease because the first number increased. So math has multiplication particularly has an inverse relationship there. And so that is also, you could call it seesaw motion, whatever you want, but hopefully you remember this. So I want you to notice that temperature is not listed here. So big tigers, this is Boyle's law. So this is actually a Boyle's law chart. If you ever graphed Boyle's law in chemistry or saw a graph of Boyle's law, it looked just like this. So we've already seen 2 of the gas laws. So look at that, chemistry came back up. Who would have thunk it? Now, I want to show you data set 1, and you're going to notice a very similar thing. You're going to notice volume and pressure data. I'm going to tell you right now, it's going to look just like what you saw there. And so one of the things we're going to establish today, and this is actually something I suggest that you write down. So if you don't have something to write down or type on, I'd go ahead and open something up, because I'm going to give you something like a flow chart that's going to have you check boxes as you go. So when you see a data set, your first question is going to be, and this is the first first thing that you are going to have as an identifying thing as far as what you're going to do is you're going to look at the two data sets, and your first question is, do they move in the same direction? So that's your first flowchart piece, is does the two sets of data move in the same direction? And your answer here is what for data set 1?
No.
No, they don't move in the same direction. So this is actually, the reason I give you this is because inverse is actually a special one that shows itself immediately in that nature. If one of the variable sets is decreasing as the other data set increases, that means that you have an inverse relationship, and you can stop trying to figure out what kind of graph you're going to have. So the second that you see you have one going up as one goes down, you're going to look at which one goes up and which one goes down, and you're going to graph appropriately. So they've got it set up to where V goes on the x-axis and P goes on the y. If you didn't read the instructions, the first column goes on the x, second column goes on the y. So I'm going to go ahead and draw that in. So we've got P right here. I'm going to increase my stroke thickness so I can actually see that's much better. And then I've got volume down here. So as volume increases, pressure decreases, and I'm going to see a curve that looks something like that right there. And if we refer back to that, what do you know? We've got that same curve right there. And so this is just data that is giving us that curve. So I want you to understand what linear means so that you can know why we're about to do what we're going to do to treat this data. Okay, so we have one going up as one goes down. Is that how a linear relationship progresses? What is the tendency for a linear relationship? There's two things that must be true for two data sets for them to be linear, for their comparison to be linear. What are they?
Is the rate of change constant?
There we go. So the rate of change must be equal to each other, even if they're not constant. And then what else?
They have to move in the same direction?
There we go. They have to move in the same direction and do so at the same rate. And that's your goal. That's all you're doing here, is you're trying to get them to move in the same direction and at the same rate. And so everything you're going to do today is to meet that end. So how am I going to do that here? Your first thing is they're not moving in the right direction. So I'm going to have to take one of these variables and make them move in the opposite direction. And in order to do that, so let me give you an example. All right. You see this? Right here? What shape or letter would you say that looks like?
V.
V. Now, how would I make it look like an A?
Flip it over.
You're going to have to flip it. All right? That's what inverse does. If you've got this tendency of going down, you have to flip literally everything by dividing by 1. All right? So you're going to divide, or not dividing by 1, excuse me. That would just give you the same numbers. You're going to divide 1 by each of the numbers, and that's what's called taking the inverse. So that is represented as one of two ways. It's either represented as 1 over V, or V, does anyone know what the other way to represent an inverse?
-1?
To the negative. Yeah, I don't know why I started writing 2. Yeah, to the -1. So V raised to the -1. These both mean the same thing. Because anytime you raise something to the negative, you are you're putting it into the denominator of an increasingly complex, as you go further into the negative, increasingly complex fraction. So what's that going to do to your numbers? In the same way that it turned the V shape to an A, it's going to flip all your values. All right, so if you have big numbers and you divide 1 by a big number, it becomes a small number. If you have small numbers, meaning less than 1, and you divide 1 by that, it's going to become a larger number because it goes into 1 multiple times. So let's explore that. So what's 1 divided by 1/10? 10. 10. Right now, I'm not going, when we get to decimals, I'm not going to draw the decimals in because they are a pain in the butt to erase, but just listen to me. I might not write it explicitly. So what's 1 divided by 1/2?
2.
2. What about 1 divided by 1? 1 divided by 2?
0.5.
0.5. I'm just going to draw that 5 there. What about 1 divided by 4?
0.25.
1 divided by 5?
0.2.
1 divided by 8?
0.125.
There we go. So if you never remember that, half of 25 is 12.5. And then 1 divided by 10?
0.1.
0.1. And then what do you notice happened to our data? What happened?
It's now linear.
Well, not only is it now linear, this data set has now completely changed its orientation, and where it was increasing, it is now decreasing. And so because of that, your data set matches. Your data set matches in direction. And so that means as one increases, the other increases, as one decreases, the other decreases, and they both do so at a roughly even rate. Now, it's not like that does not initially look linear, right? From 40 to 8, nothing about that screams linear, especially once it drops down to a 4 and then a 2 and then 1. So that doesn't initially present itself as linear, just looking at the jumps individually. But the fact that you're seeing the same kind of jumps for each of these means that they're moving in the same rate, in the same direction. And at that point, that now makes our new graph linear. So what would I call this set of data right here? If this was V, what would I call this set of data that I wrote next to it?
Can you rephrase that question?
If the first data set is called V, which is this variable right here, which is that initial typed out data, this data that I wrote next to it, what can I call that? What's that new variable?
1 over V.
1 over V. And so in order to get that straight line, I had to plot this data. And so instead of P versus V, this is now P versus 1 over V. This is your new x-axis, and this is what you're going to use in your equation. So I want to remind you that you cannot determine a slope from a curve, so you can't even begin to use these variables in your slope-intercept form. However, now that you've treated your data, you've gotten a linear line, you can totally determine a slope and then use the equation, plug in your variables here. And so your base form is y is equal to mx plus b. Your y value is p. Your x value here is 1 over v. And you're just going to plug those in to the original equation. And you're going to get the equation that p is equal to, let me see if moving it closer makes it easier to write. What did I do? Sorry. P is equal to m 1 over v plus b. So this is your new equation. You could also write m over v. That would also work. But let's check this, okay? Now, your goal here is not to determine slope. I'm going to determine slope to prove a point to you. All right, so if it's a constant rate, that means that the slope doesn't change, so I can pick any two sets of points. So I'm going to pick these two right here. All right, so we're going to do y2 minus y1 over x2 minus x1. What's 8 minus 40?
Negative 32.
Negative 32. What's 2 minus 8 or 2 minus 10?
Negative 8.
Negative 8. The negatives cancel. 32 over 8 is equal to
4.
4. All righty. So now we have that our slope is 4. All right. So you have one of two options here. You can take your original volume data and plug it in, or you can just go ahead and substitute in the already treated data. All right, so let's just try the already treated data. So right here, 10 is our first value. We have no slope intercept. If you know anything about chemistry, you know that if you have no volume, you have no pressure. There cannot be an intercept for this graph. This is a physical impossibility. So the intercept here is 0. So we're just going to plug 10 in. And what's 10 times 4?
40.
400.
40. All right, what's 2 times 4?
8.
1 times 4?
4.
There we go. Now, I want you to look at what you could also do here. This is if you're using the treated data. And you would have had to actually calculate this out and then use that to determine slope to even prove this. But this now becomes predictable. I can take the original data, fit it into this equation, and as long as I know the slope, it's going to give me any pressure that I want. So for instance, if I use 10 here, I know that I'm going to have to put 10 under 1, right? Because that's how this is stated. And I can just go ahead and pop m on top, multiply that m out, and I'm going to get 4 over 10. And 4 over 10 is 4/10. And that's our answer for the pressure at that volume. And so this has now produced a predictable formula that you can use with any original data. As long as you plug it in and you know the slope, you can then use it to move forward. All right, now let's look at the next thing. So I'm going to spend the rest of the time kind of breezing through this so we can make sure to have plenty of time. And so this is exactly what we just saw, that P is equal to M1 over V plus B. And then where B is equal, so P is equal to M over V. When rearranged, it equals, and the mass is constant, that PV is equal to constant, that the product of pressure and volume is equal to a constant, which is known as Boyle's law. So this is actually how you determine that fact in Boyle's law. So now let's look at this curve. All right, and this is where our handy dandy ruler is going to help us out. All right, so we've got a graph here, and this is described as a top opening parabola. All right, and a top opening parabola is one that looks like half of a parabola that's opening toward the top. All right, and now I want you to remember, what scenarios did we need for something to be linear? It must be two things. What are the two things that those data sets have to have in common in order to have a linear relationship?
Same
Constant
direction.
rate in the same
rate of
direction.
change.
Constant rate or the same rate. I will tell you, it does not have to be constant. If they're both squared, or they're both square roots, or they're both cubic functions, all that matters is that they move at the same rate as each other. All right, because you will not see many functions that move at a constant rate. Very few things are that simple. Most things are some kind of a power function. All right, that's how the world works. That's why you need calculus. Anyway, we're looking here, and what is the case? Are they both moving in the same direction? Just looking at this graph.
They are.
They are. So it's got a positive moving slope area. So yeah, it's moving in the same direction, but are they moving at the same rate?
No.
No. Which one's moving faster just by looking at this?
X.
Yeah, the X value, well, it's going to be the distance values. So the Y values here. So let me try to give you an example right here. So if you're looking at data set 2, the answer would be X. All right, so let's just look at these two data sets. Now, I want you to compare the two, and I want you to tell me which one seems to be growing at a faster rate.
The Y.
The distance.
The distance, the one that's listed as meters. Now I'm going to give you an example. This is a physical demo. If you do not get it, that's okay. This has helped clear it up for me and a lot of other people. And I really want to stress this. This is a ruler. Can you guys see me? So down here to the bottom and to the right. So bottom to the right is the x-axis. Up and vertical, or left and up, is going to be the y-axis. So generally, a linear line is going to be somewhere between those two, right? And when we say that the variables grow at the same rate, all right? So what that means is the variables grow at the same rate, meaning that this one grows at the same rate as this one, and the pressure on the line is equal on both sides, so it forces the line to be straight. Does that make sense if you think about it like pressure? So neither one is pulling any harder than the other. All right, so let's look. Which one is our y value? That's going to be x right here, right? This is t. So which one's pulling faster or pulling harder by growing faster?
X.
X. All right. So what that means is that it actually pulls our data toward that column. All right. It's going to physically or mathematically pull the curve toward the axis that's growing faster. That's what an exponential suggests. So if I wanted to get this curve that's all the way pulled up toward the top to come back toward the center, what am I going to have to do to it? You have one or two options, and one of them is correct. So if I got it to curve upward by pulling faster on the Y value, what am I going to have to do to pull it back down toward the center?
To pull faster on the X value.
There you go. You're going to have to make the X values grow faster, and you're going to pull it back to normal. So if this has a squared functionality, or it seems to be growing exponentially, in order to correct for a graph that looks like that, you're going to have to pull harder with the X values. So that means you're going to have to make these X values down here, or let me specify your independent variable down here on the X axis. You're going to have to make that data set grow faster in order to pull the curve closer to that axis and correct for the pulling that's already showing up right there toward the Y axis. So that means squaring all the values of T here, which is exactly what they suggest to do in our reading, right? They suggest squaring T, and that ends up giving you a positive linear line. All right, and then what's your new variable down here that goes on the x-axis?
T squared.
T squared. There we go. So we got T squared right here. So when you rewrite your equation, what's it going to look like? What's your Y value that you're going to put first?
X.
X, all right, is equal to M. And then what's my new adjustment for the X value?
T squared.
T squared plus B. All right, now I can also do this really quickly. I'm just going to square two of them to show you. 2 squared is 4. 3 squared is 9. And let's find the slope really quickly. So 27 minus 12 is 15. 9 minus 4 is 5. That slope is 3. All right, so we got 3 as our slope. So let's take any t value. We don't have a y-intercept, so it's 0. And let's just plug it in. Let's pick 5, okay? Or you can pick 4, but try it out. You've got a slope of 3 and an input of 5. What's your x output, or your output over here on the other column? 5 squared is 25. 25 times 3 is 75. If you try that for every single one of these, it will result in the coinciding y value. So this has now become a predictable model. I'm not going to do data set 3. I will show you data set 4 though. All right, so which one seems to be growing faster? Which one seems to have a faster growth rate? T or V?
V.
Which one seems to be growing
T.
faster? T, because V doesn't change. It's constant. It's 10 every time. But this one goes 0.4, 1.5, 1.5 again. No, that's not right. 1.9, 1.11, 2.1. I can't count. I'm sorry. 2.1. So each one seems to increase in its increase. So this suggests an exponential function. So if T is growing faster, which way is the data going to get pulled? Which way is that line going to be pulled? It starts here, and your x-axis is pulling faster. What's going to happen? If your x set of data grows faster, what happens to the line?
It's gonna like go downwards.
It's going to pull it toward that axis. And so as it adds extra pressure and pulls it down, all right? And then in order to get this to become linear, what am I gonna have to do to correct for that?
Pull harder on the other axis.
You're gonna have to make the other axis grow faster so that you can correct and pull it back in the other direction. So your initial values here are gonna look something like that. That's a side opening parabola. And in order to fix that, I'm going to have to square my y value. So I'm going to have to do v squared. Now, these are pretty easy to square. All right, but v squared goes there, and t goes right there. And so your new line is going to look like that right there. If you were to square these, I'm just going to say 100 and 400, and then you took the difference between them, you would find that to be 300. So it'd be 300 as your difference for these two values. And 1.2 minus 0.3 is 0.9, which is 333.3 repeating. And so that's your slope. If you were to plug that in, I'm going to let you come up with a mathematical expression here. You're just going to need to make sure to replace your y value with the correct y value, put in m and then the x value plus b. And if you want to prove it, plug it in. That's your slope. You just plug that in. So data set 3, they both seem to be moving in the same direction, and they both seem to have a pretty steady rate of change. So I want you to think about what that might mean for your first graph. And if it is linear, you don't have to do anything, and the second graph is going to be linear, and you don't even have to adjust the variables. You just have to plug those variables for x and y in. And then data set 5 and data set 6 are some version of what we just saw. Okay? Do we have questions?
I have one question.
Yes.
Are we going to have access to this?
My drawing or the video?
The drawing.
No, because I'm showing you this in class right now so that you can copy it down real quick if you need to fill that in. And then you need to be able to take what I showed you, because I just showed you every example except for linear, and then figure out what the last two are.
Okay.
Alrighty. And then what was your question, Talata?
Is it possible that you'll have to use multiple, will you have to modify both the x and the y to get a linear?
It's very unlikely you're going to see that, but I'm not going to say no. Be a very rare occasion. You're going to be dealing with these 4 graphs, really. And then linear.
But on this worksheet, I won't have to do that.
Nope.
Okay.
So your first question, I told you I'm going to give you a flow chart. Your first question is, are they moving in the same direction? And you have 2 answers, either yes or no. If they're moving in the same direction, you start asking other questions. If the answer is no, then you know it's inverse, and you treat by taking the inverse of the x value, all right? So if it was a no, they are moving in the same direction. Your next question is, are they moving at the same rate? Are they growing at the same rate? And so you're going to ask 2 questions. Is x growing faster, or is y growing faster? Okay, so that checkpoint of are they moving at the same rate, the first thing you'd mark off is whether or not it's inverse. And so if they're moving in opposite directions, it's inverse, handle it like an inverse. Your next question is, if they're moving in the same direction, are they moving at the same rate? If the answer is yes to that question, then you're dealing with a linear graph, and you are easier than the first version of the inverse. And then you've got 2 options left. Is the y column growing faster, or is the x column growing faster? And then depending on your answer to that, you're going to hone in, all right, then that means that I'm going to have to square the other non-exponential data set. And that's going to pull the curve back toward the center. The other option is to take the square root of the squared function. But what I'm going to tell you is that this is simply stating powers. And so the powers mean that it could be cubic. It doesn't necessarily have to be squared. We're generally going to see squared functions, and for the most part, you're not going to see many cubic anywhere in this class, especially because we're dealing with algebra, not calculus. But just to let you know, it just simply means that one's growing faster than the other, exponentially so, and you're going to have to use exponents on the non-exponential set of data in order to correct the curve. So again, I'm going to remind you, if it's pulled, if the x values seem to be growing faster, it pulls the curve toward the x-axis. If the y values seem to be growing faster, it pulls the curve toward the y-axis. And whichever directions it's curving in the original, you're going to have to square the opposite axis in order to bring it back to the center. It's mathematical. This is a really good example of mathematical pressures on a graph. And it's really rates of change. If one outstrips the other or grows faster, it's going to provide more negative pressure toward it. And it's going to pull the graph there. So if you guys don't have any more questions, you've got about 8 minutes left in class. I want you to work on this. Now, let's say you don't finish. You get to number 4, you get to number 5, and you still have 1 or 2 left. I want you to turn this in, and I want you to turn this in complete and as accurate as you can make it. All right? So that means that even if it's a little bit late, even if it's a little bit after school, I still want you to turn it in. I don't want any garbage. I want you to actually try this and get something from this activity. Because what we're going to do, actually I'm going to have to use the last 4 minutes of class for a video. So if you don't finish, you've got to the end of tonight. I know the due date says like 1:15 when class gets out, right? We get out at 1:15, right?
1:45.
We get out at 1:45? What? We've got so much more time, guys. I'm over here thinking I only had like 7 minutes left in class. I'm like, how in the hell am I gonna do this? Excuse my language, but I was freaking. All right, so we are good to go. So you guys got plenty of time. Take your time. You're gonna finish in class. All right, I'm gonna stop sharing. Thank you for being more put together with your scheduling than I am. Whomever it was that corrected me. Yeah, I guess it would make sense if, you know, we started at 12:15.
All right. So, Mr. Sellers,
Yes.
what I noticed, unless I did this completely wrong, right? With data set number 6, when you inverse the X values to make them go at the same, in the same direction, it's still a parabolic curve.
Slightly side opening.
Slightly like up, going up like this, it slightly curves upwards towards the y-axis.
Let me see really quickly. 6.
I got the same result.
I don't know if you can see it, but like,
Hold on. Let me go to your screen. Okay, I definitely do see what you're saying. So I want you to look particularly at the last section of data.
mhm.
So that last section of data looks kind of linear, right? So I'm going to tell you right now that this is, again, square peg in a circular hole. We are currently using algebra to do things that calculus does much better. And so curve fitting, if you read the very first paragraph, it says that we're going to be doing something that's pretty accurate and works most of the time and really helps you see that in order to get a predictable graph out of it, you're going to have to treat a set of data, replace that variable in the slope intercept, and then determine slope from that new set of data. And it's not perfect because we're using algebra. And I'm going to tell you right now, we're going to run into lots of areas where there's gaps, and that's one of the gaps that you just found. All right, so for the most part, if you were to zoom out on that function, you would see that that main section looks pretty linear. And it kind of has, it still has a parabolic. That's because there's not, it's not a perfectly relatable inverse function there. Because is that the question you're asking, if you have to treat it twice?
Mhm.
All right, try treating it twice and see what happens. So if now you're seeing a top opening parabola, treat it like a top opening parabola and see if you get a new linear version out of that.
Mhm.
So, Mr. Sellers, is it like that for a lot of like the ones where you square it? Because when I double checked like with Desmos and I zoomed in, and a lot of them ended up being non-linear. So I thought it was wrong because of that.
I 100% understand what you're doing, and that's why we are not actually plotting the points. That's why this isn't a graph. This is a sketch, because it's more so here to teach you, because these data sets don't fully adhere to that exact square function. It's like So did it become linear?
Yeah, it's a straight line now.
All right, so that would be an example where you have to do it twice. And so if you know anything about calculus, there's certain, whenever you get certain functions, you have to treat them twice because the relationship is not as simple as treat it once, it's linear. And so what you just discovered was something similar to a second derivative idea of, in order to get what you're looking for, in order to get that relationship that we're searching for, you have to go one step further. And so you did a good job with noticing that. Now, I want you to understand that if we were in a calculus-based physics course, the algebra here would still be useful, and we would still use it. So you don't ever get rid of the algebra in physics, because it's how you talk about variable relationships. But it's the rates of change and it's the changes of curves that really become much more intuitive. And so you're going to see every once in a while, like that particular example. And then RJ, if you found in Desmos that, you know, it's not perfectly linear, what's the closest thing it is to? And you might have to treat that data set a second time. Does that make sense? And so that second set is something that is not something I stress, because you could do it another time and get more accurate, or and then go too far. You have that option. So I wanted you to just, I didn't want to overwhelm you and tell you, you might have to do some of these twice. But I'm glad that you guys noticed that trend. This is the intro to something we're going to be doing all year, which is taking complex data sets, finding a relationship by plotting them on a graph, and then determining how we're going to linearize that data. And so if in the case, like what we see right there with the radius and the electric force that you're being shown in data set 6 in newtons, where you see an inverse relationship, and what you're noticing is because R is not accurate. What you're actually going to see, so I'm going to share my screen really quickly just so I can show you something. And if you remember, if AP Chemistry should have taught you this at some point, but do you guys know Coulomb's law? Did you mess around with Coulomb's law at all?
We were getting to that point, but then we had to start studying for the actual exam. Like, she doubled down on stuff that might actually be on the exam.
All right, Coulomb's law states, and you will actually learn it in here, that the electric force between any 2 point particles, which is what we're going to talk about with, you know, electric charges, you start talking about point particles in the same way you start talking about point mass. It is equal to Coulomb's constant, which is a corrective number. This number is just so that it comes out to newtons, multiplied by Q1, which is the charge of the first, that's supposed to be an X, times Q2, all over R squared. All right. And so if you know anything about the force of gravity looks just like this. You're going to see this equation pretty quickly on. Big G is, sorry, let me erase that real quick. So G times M1, M2, R squared. This is just a really interesting relationship here, that it just happens to look exactly the same. If you know anything about Richard Feynman, this relationship was what he spent a lot of his time on, trying to figure out why these looked the same, why the electric force between 2 point particles was very similar to the force between 2 point objects in space as far as gravity is concerned. But the point being is, I want you to notice, what value do they give you in this chart? They give you electric force and what?
Radius or distance.
So what's missing from that equation I just showed you?
That constant value, or the K or the G, or
Not so much. I want you to notice, as far as R is concerned, what's missing?
the squared.
The square, and that's what you found when you found your parabola. Does that make sense? So what you did is you actually found that there was a parabolic relationship between this and r because they never mentioned r squared. If they had had r squared here, you would have noticed it would have gone straight to the linear form. But instead, there's this in-between step where you do the inverse relationship, you find this relationship that relates to the square here, and then based on the fact that you've got a square there, you then have to square the force of the electric force here in order to get that linear relationship. So there was a square hiding, and that's why I don't bring it up, because I told you that like technically I might have just lost someone here. If you guys don't know, do you see where that relates and why there was a second treatment necessary in order to get a linear relationship? Because the variable they gave you as the relationship doesn't include the square. And so the direct relationship that actually exists in that equation is squared. It's a product of, or it's an inverse of the squared distance. So that means that the further out you get, the quicker it drops off, and it drops off exponentially. So same thing with gravity. The further away from something you are, the weaker the gravitational force is. And so because that initial variable did not include the square, you end up with that parabolic showing up, because it's the data is real data. Like, that's real data. If you guys didn't realize, every single one of these data sets represents something you're going to learn in this class. So I'll just tell you, we won't talk about pressure a lot, but this is pressure and volume, so that's the gas laws. Data set 2 is distance and time, so that's just a position versus time graph. Data set 3 is area, or excuse me, months and pounds. So this would be like weight gain or weight accumulation. This is just a rate of change example. This one is time versus velocity, which is the V versus T chart, or V versus T graph, which is pretty commonly what you're going to use. And then the last two are actually opposites of each other. They both refer back to both of those equations I showed you. So if you remember, I told you one is about gravity and one was about force of electric. This right here, does anyone know what data set 5 is representing?
I'm guessing it's something related to, because AU is astronomical units and years, so it's something with light years involved.
Okay, so maybe not. Maybe no, that's actually years. Those are calendar years, Earth years. So I want you to look at particularly what's one AU. What does one AU mean? What's an astronomical unit? What's the basis for that? Does anyone know? You're welcome to Google it.
So it's the distance from the Earth to the Sun?
There we go. It's the exact distance between the Earth to the Sun. Now I want you to notice the third object from the top of the chart. What is its distance in AU?
It's one.
It's 1. And how many years?
That's also one.
All right, so what do you think that particular data right there, 1, 1, represents? If AU is the distance from the sun, what is exactly 1 Earth distance from the sun from the sun?
1 rotation?
1 year, 1 rotation.
Of what? Of what body?
Earth?
Earth. This is the period of rotations around, or revolutions around the sun. So what you see here is how many this is old data, by the way. There are 9 data points here. So each one of these represents one of the 9 original planets. So you've got Mercury, excuse me, let me try that again. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. And this is how many years it takes for them to make 1 full trip around the sun. So this big T stands for period. That means 1 oscillation, 1 full rotation, 1 full return to the same place. And then R is the radius of center of mass to center of mass. So the center of the planet to the center of the sun. And we set Earth at the one distance so that we can measure everything else in reference to that. And so you're going to see that, each one of these is representative of another planet further out. So this right here is gravitational information. And I'm not sure what kind of a relationship you guys noticed there. But you're going to notice you had to do something to one of the data sets, and it might even refer back to the relationship I showed you in the equation we saw earlier, right? So what data set did you have to square for data set 5?
The R value.
The R
Or
value.
the-
Now look at this right here. R value is squared. So in order to get a linear relationship between those two, you have to have a squared R. And in the same way, they completely left the square out for the force of electric, so it leaves you with a parabolic function that you then must linearize by squaring your other one right there. So this is just to let you know, these are hinting at much larger things that we're going to get to later in the semester. You will know these by heart by the end of this. Like, I didn't have to refer to a equation sheet, and that's a lot of variables. But it'll start to make sense the further we get in. All right. So, like I said, the last 5 or so minutes of class, which is, still 20 minutes out almost, or about 15 minutes out, I am going to show you guys a video that gets you ready for the graphing assignment / lab we're going to have on Friday. But I just wanted to let you know that that data set is actually, all of those data sets are based on real physical data. I've got somebody already trying to join my physics class at 1:19. That's what actually threw me off. Like, I was like, I'm pretty sure I got plenty of time. And then, like, I got an email that's like, such and such joined your physics class. I was like, wait a second. What time do we get out of here? All right, so just so I know, let me get a thumbs up in the participants tab if you have finished the homework. So if you're done with it, give me a thumbs up, just so I can kind of check. All righty. All right, so you guys keep on working. Again, I'm going to give you pretty much the whole class period. We're going to end on a nice brain break. So do you guys like cathartic videos? Videos that are aesthetically pleasing? Do you like time lapses? Well, we're going to combine all of those things together, and hopefully it's going to help you de-stress. All you girls are smiling. The guys are like, I'm not going to tell you I like that. I'm not allowed to like that societally. Uh,
Mr. Sellers,
yes.
can I ask you a question about number 3? I just have like something I'm a bit confused about with it.
Go ahead.
In terms of like not like I have done it, but I just confused about one thing, and that's you said just a few minutes ago that you should like in the case of where you have to square it, you would square the side that like doesn't increase as much. That's what I got at least. Is that correct?
Right. Yeah, you're gonna the one that's growing slower, you have to make it grow faster.
Well, with data set 3, where it goes, like 1, 2, 3, 4, 5, 6, 7, 8. When I don't know if this is because of the calculator I used, but when I squared it, it did like it formed another like Well, it wasn't linear to be. I think it was hyperbola it formed. It might have
Right.
been,
That will likely form a hyperbola because you'd be squaring your x value there, which would make your x value grow faster, which would end up bringing your curve closer to your x-axis. So it probably gave you something like a hyperbola. And so the issue there is that you took it a step too far. And I told you if they grow drastically differently. So I want you to look at the data set, and you're going to notice that the first set of data for months is very clearly growing at a linear rate, very steady rate. And then if we look at pounds, it doesn't initially present itself as linear just because each jump is not exactly the same, which is what you see for, like, for instance, the velocity values for data set 4. However, if you start to look at each of the jumps, so from like 7.3 to 9.4 is going to be 2.1. And then it's 1.1, and then about 1.5, and then 1, and then 1.3, and then 0.9, and then 1.5. And so it seems to be going up and down, but if you were to take an average of each of these jumps, each of these changes, they come out to be roughly about 1.4, 1.5. And so in this case, even though it's not exact, it presents itself largely as linear because it's not growing exponentially. It might not be growing constantly, and I'm not at all saying that it is, because the rate at which it grows changes almost every single interval. However, the general trend that you're going to see with that weight data is that it's not growing exponentially. That part does kind of show itself. And so you're going to have a roughly linear relationship here. And again, I want to stress to you guys that this data isn't perfect and that it's not going to fully represent. If you were to graph this on your calculator, and I know many of you have the tendency to want to do that because it's a really good tool, and I encourage that, especially later on. But in this case, it actually might be getting in your way because it's not going to immediately look like a straight line. But if you just look at the rate at which they're growing and the fact that they're both growing in the same direction, you're going to get roughly a linear line, and you're not going to have to treat this data. So it's already linear, and you can get a roughly predictive equation just by saying that the W is equal to MA plus B. And you'll get, and if you were to find, and of course, you'd want to probably take a larger chunk to find the slope here because of that variation in each interval. You'd probably want to take like the whole interval and get an average so that you'd get a little bit more representative, so it's more accurate. But because that data is kind of shoddy, it's not going to be perfect. But perfection is not at all what we're striving for. This is more a skill building activity than a precision activity. But thank you. That's a really good point. Is that cleared up?
Yes. Okay. Thanks.
Awesome.
I'm just expecting it to be like exactly linear, and that confused me when I was doing this. I was like, these aren't completely matching up, and it's like to a straight line. But if you're saying it's fine that they're not, then I'm good.
You're like, I'm not going to do extra work. We're good. Yes, I love it. So thank you for bringing that up. You guys have been making such great points. I love it.